Okay, we're going to get started. I understand there are representatives from industry and from Natural Resources Canada in attendance or joining us by teleconference for this item. And they will be available for questions from the Commission after the CNSC staff's presentation. So, Mr. Robertson, over to you, please.
Good afternoon, President Velshi, members of the Commission. My name is Hugh Robertson, and I am the Director General of the Directorate of Regulatory Improvement and Major Projects Management at the CNSC. Due to the scope of the content that is being provided today on small modular reactors, or SMRs, this presentation has a number of presenters. With me today are Mr. Christian Carrière, Director of the New Major Facilities Licensing Division, and Ms. Stephanie Hursted, a Project Officer from that division. We also have Dr. Dave Newland, Director General of the Directorate of Assessment and Analysis, Ms. Melanie Rickard, Director of the Assessment Integration Division, and Mr. Daniel Duchesne, a Technical Specialist from that division. Additional CNSC staff experts are here and are available to answer any questions the Commission may have. We also have in attendance representatives from Natural Resources Canada, Atomic Energy Canada Limited, Canadian Nuclear Laboratories, New Brunswick Power, Ontario Power Generation, Bruce Power, Terrestrial Energy, and the CANDU Owners Group. This CNSC staff presentation is a follow-up that builds on the Commission presentation we gave in February of 2014, CMD 14-M8, the evolution of nuclear reactor technologies. At that time, CNSC staff gave a three-part presentation. The first part provided an overview of reactor design evolution and how safety considerations are reflected in design. The second part gave an overview about what an SMR means from a regulatory standpoint, and the final section provided an overview of the pre-licensing process that allows a vendor design to be reviewed by CNSC staff. There have been a number of developments that have occurred since that time. The main purpose of this presentation is to share the current state of affairs and answer any questions that the Commission may have. Today's presentation begins with background information that speaks to what an SMR is, the current climate in Canada for these technologies, and the related international activities that the CNSC is engaging in. We will then provide an overview of some generic SMR technologies that CNSC staff are seeing, as well as an update on the pre-licensing activities that allows a vendor's design to be reviewed. Finally, we will highlight the CNSC's readiness strategy for SMRs. I will now turn the presentation over to Mr. Christian Carrière, who will provide information on the first item.
Thank you, Mr. Robertson. Madam President and members of the Commission, for the record, my name is Christian Carrière, and I am the Director of the New Major Facilities Licensing Division. My division is mandated to lead licensing and compliance activities for all new nuclear reactor projects in Canada, including small modular reactors. This includes managing the conduct of vendor design reviews of new reactor technologies under a project management framework, coordinating pre-licensing engagements with applicants, participating in public outreach and international cooperative efforts related to new reactor technologies, and leading organizational readiness activities for these projects. We will go quickly through the main discussion points that were presented at our last appearance before the Commission in 2014, and we will update the Commission on what has happened since then. Historically, the regulatory framework related to nuclear reactors has evolved along with technological developments and accumulation of operating experience. This is not limited to Canada. The early prototypes and first-generation commercial reactor designs were supported by scientific experimentation carried out in national laboratories, coupled with experience from conventional steam power plants. At this time, the scientific and engineering community was relatively small, but already establishing fundamental safety principles such as defense in depth in design and operation. The analytical tools at the times were good but rudimentary. This, coupled with lack of operating experience, led designers to address uncertainties through implementation of conservatism in design and establishing of safety margins. Early regulations were based on fundamental safety objectives, with few prescriptive requirements because operational experience was either not available or limited. As the next generation of reactors were produced, the regulatory framework evolved. As operating experience from construction and operation grew, regulatory requirements became more prescriptive and specific to reflect accepted practices for those new technologies. New reactor designs were evolutionary at that time from previous generations, and such prescriptive requirements provided designers and operators better regulatory certainty. Today, with respect to advanced reactor technologies, we are once again being faced with a situation where operating experience is limited and prescriptive requirements may need to be revisited. In a nutshell, we may need to go back to basics. The value of our more objective-based approach to regulation, which we believe continues to apply to new reactor technologies, has been recognized nationally and internationally. The term small modular reactor has generally been adopted internationally by the nuclear industry. It is not a separate category of reactors and remains, in fact, a Class 1A nuclear power plant under the Canadian nuclear regulations. The IAEA has defined SMRs as reactors that produce up to 300 megawatt electrical. Generally, SMRs differ from currently operating water-cooled reactors both in design and deployment strategies. On the design side, depending on the intended application, they may vary significantly in power levels from a few megawatts electrical for remote application to several hundred megawatt for reactors connected to the grid. Size-wise, units could fit in a small building comparable to a house. Larger units could be as big or bigger than the now shut-down Douglas Point reactor at the Bruce site, which is approximately 1/4 of the size of the Bruce A or Bruce B units. Several SMR designers propose to use multiple novel approaches in their design. The goal of these novel approaches are typically to improve safety performance, increase efficiency and reliability, improve economics, proliferation resistance, and physical protection. The intention of several novel features in a single, the integration of several novel features in a single design presents great potential and new opportunities. However, it also presents challenges in predictability of overall performance and in demonstration of the safety case. SMRs can also differ substantially in deployment concepts. One example is security by design. For instance, some proponents are proposing to locate the reactor below ground so as to reduce the likelihood and impact from aircraft crashes. Other novel deployment strategies include autonomous operation with remote intervention and transportable reactor or relocatable reactor cores. Some propose extensive use of factory construction facilities and or reactor modules that may be sealed at the factory. In light of these considerations, SMR should be viewed as smaller reactors. They do present some new challenges, particularly with the various design and deployment approaches that are being proposed. However, the Canadian regulatory framework is flexible based on decades of operating experience and can be applied to advanced reactor technologies. Ultimately, all safety claims will need to be demonstrated by suitable supporting evidence. Today, we are looking to the future while building on our foundation of operational experience that's been assembled both nationally and internationally. Many of the proposed SMR designs are based on concepts that were originally developed in the 50s and 70s, 50s to 70s. These various technologies, including new approaches and innovative features, were in many cases tested to some extent in prototypic facilities. As such, a fair amount of operating experience with these early prototypes was acquired and remains relevant today. Concepts included reactors with different fuel, such as metallic or fuel in liquid form. Different moderator material were used, or reactors used were operating the fast neutron spectrum with no moderator at all. And finally, different coolants, such as molten sodium, lead, or gas. Each of these new technologies propose new ways to ensure safety by use of more robust fuel or integration of passive and inherent safety characteristics. These designs showed promises in the past, but today the design work and research and development are still needed to support safety claims. Regardless of the technology, the CNSC has practices in place to review such design and ensure safety. Internationally, there has been a growing interest in potential application of SMRs, in many cases as a component in addressing climate change initiatives. Some of the prototypic design tested in the 50s, 60s, 70s, and even 80s were faced with challenges arising from technical limitations or did not compete with water-cooled technologies. Nowadays, in light of advances in materials and analytical methods and new market needs, some of these designs are being revisited as potentially achievable or cost competitive. Market-wise, these designs are also being considered where larger traditional reactors are not practical, with regards to size and capacity of the existing grid or where there is no grid at all. If we look to early and novel Canadian designs, the nuclear power demonstration reactor and the Douglas Point generation station were examples of early reactor designs. These units had a lot in common with SMRs that we are seeing today. Designers at the time were also faced with similar challenges: a lack of codes and standards, uncertainty of behavior, and definition of safety margins, amongst other issues. Douglas Point in particular was intended to be a template for future repetition, the first unit in the fleet, and some elements of the design were modular. The overall approach appears to be a historical reflection of current plans and a success in deployment of a technology. This slide presents two examples of early international designs that would fit the IAEA's definition of an SMR. Calder Hall is the ancestor of the US gas cooled fleet, while Dresden 1 reactor is one of the main ancestors to the world's boiling water reactor fleet. These are just examples that has been, these are just examples. There has been a wide range of nuclear technologies tested prior to the establishment in the 70s and 80s to the existing water-based fleet. Across all of these early designs, uncertainty was addressed with increasing safety margins. The same approach of increasing safety margins to address uncertainties can be applied today to the new designs. For example, by having increased instrumentation, thicker walls for vessel, using removable samples, or restricting the operating envelope. Turning now to recent projects, as early of July 2018, Rostechnadzor, the Russian nuclear regulator, approved work on the floating nuclear power plant named the Academic Lomonosov. This is a pair of 35 megawatt electrical water-cooled reactors that are intended to replace the 4 12 megawatt electric Bilbino reactors. The barge reactor are being fueled at this stage, as of today, and is being transported to its destination. Commercial operation is planned for 2019. There is also an example, this is just an example, and other projects are planned or underway in China, Argentina, and South Korea. I will now turn the presentation to Ms. Stephanie Hersted, who will provide some information on recent developments in Canada.
Thank you, Mr. Carrier. President Belshi and members of the Commission, for the record, my name is Stephanie Hersted, and I am a project officer in the new Major Facilities Licensing Division. We will now discuss some recent developments that have occurred since the last update to the Commission. There has been significant interest in potentially deploying small modular or advanced reactors in Canada. Key stakeholders have shown interest, including existing power utilities, provincial governments, and the federal government. CNSC staff have worked to ensure we are ready to review and license new reactor technologies of all types. Our recent work has been motivated by a number of drivers that are highlighted in the following slides. Please note that on this and the following slide, there are two minor errata that will be corrected verbally. At the federal level, language has changed and nuclear is recognized as a non-emitting form of energy generation. Natural Resources Canada is promoting government expertise in clean technologies and is engaged with the provincial governments. In June 2017, the House of Commons Standing Committee on Natural Resources produced a report titled "The Nuclear Sector at a Crossroads: Fostering Innovation and Energy Security for Canada and the World," which recommended, and I quote, "The Government of Canada continue to support the development of small modular reactors, recognizing the potential for SMRs to provide clean and reliable power to remote and northern communities and open new areas to economically valuable resource development." The government agreed with all recommendations that were made in the committee's report. One key statement was that the federal government would use its convening powers to bring together a dialogue to develop a Canadian roadmap for small modular reactors. This is a Canada-wide approach including provinces, territories, Indigenous peoples, utilities, environmental experts, and academia. The CNSC is participating in the Canadian SMR roadmap in its role as the Canadian nuclear regulator. The CNSC is observing and providing clarifications with respect to regulatory process and technical issues. Please note that the Canadian SMR roadmap report will be finalized this October with the intent to make the results of this report publicly available. This is contrary to what is indicated on the slide, as should the report be given to Cabinet, it would remain under confidence. At the provincial level, there has been significant activities related to small modular reactors, particularly in Ontario and New Brunswick. The Northern Territories are also starting to show signs of interest based on addressing long-term energy challenges and global warming. On the utility side, established Canadian nuclear utilities have openly expressed interest in a wide range of SMR-related activities. Vendors have been seeking nuclear utility advice to incorporate industry requirements for reliability, safety, and economic performance early in their design process. Canadian nuclear utilities have shown signs of interest in becoming operating organizations to companies wishing to deploy SMR concepts in Canadian pilot projects. In New Brunswick, the provincial government recently committed $10 million to help develop a nuclear research cluster, including support in research and development of SMR technologies. Note that we modified the slide as it related to an OPG presentation that was made in March, not April as was originally presented and posted on the external website. There is also a new group, the SMR Technology Forum, organized by the CANDU Owners Group, that was created to discuss issues related to SMRs. CNSC staff expect this group to push for a unified approach to technology selection and regulation. In June 2016, Canadian Nuclear Laboratories issued a request for expression of interest for their small modular reactor strategy, soliciting feedback by the end of July 2017. A summary report of the responses to the request for expression of interest, titled "Perspective on Canada's SMR Opportunity," was released in October of 2017. CNL received 19 expressions of interest in siting a prototype or demonstration reactor at a CNL site. Within CNL's 10-year plan, published in April of 2017, and reiterated within this report, CNL set a goal of siting a small modular reactor on a CNL site by 2026. Based on these responses, CNL sees, and I quote, "enormous interest in establishing an SMR industry in Canada and in testing the technology through a prototype reactor at a CNL site." Following this, CNL issued an invitation for SMR demonstration projects with a deadline of June 11, 2018 for their first round of submissions. At this point, no announcements have been made. CNL has stated that they expect these assessments to be held at least semi-annually. For our SMR stakeholders, the type and scope of information that is needed is typically greater than those who are already familiar with the CNSC. External stakeholders are not limited to those who have previously engaged with the CNSC, but also includes a large number of existing organizations or departments who may be new to nuclear. With these stakeholders, their awareness and understanding of nuclear and the CNSC are quite different from those we regularly interact with. For example, it is important for them to understand that in Canada, requirements and guidance are articulated in regulatory documents, as well as codes and standards that support the regulations. This means that there is a certain amount of flexibility available to interpret and meet requirements through other means. As part of the CNSC's commitment to openness, transparency, and clarity, staff have been actively approaching potential stakeholders and introducing ourselves, explaining what the CNSC does, how we operate, and encouraging all stakeholders to ask questions early. CNSC staff have also been explaining how our existing regulatory framework tools can be used for developing and deploying small or advanced reactors, and explaining the principles that underpin our requirements, such as defense in depth, safety margins, and the graded approach. The intent is to be approachable, flexible, and responsive without compromising safety. CNSC staff continue to actively engage with stakeholders to ensure expectations are clear. In the past year, CNSC staff have seen a marked increase in requests for information sessions and other engagements. CNSC staff have increased our communications efforts and have been engaging stakeholders through vendor design reviews, pre-licensing discussions on prototypical facilities, discussions on near-term deployment of small and advanced reactors, workshops, and participation in conferences, as well as providing presentations to municipalities and the public. Throughout all of these activities, staff have been listening and considering feedback for continuous improvement. One key aspect of our communication with stakeholders was the Small Modular Reactor Discussion Paper, the associated What We Heard report, and the follow-up activities, which included 2 workshops, one regarding the use of the graded approach and a second on the nuclear security regulations. Staff have also been working to develop a license application guide for SMRs that provides considerations for application of the graded approach and the use of alternatives in consideration of different reactor technologies. The considerations for grading and the use of alternatives is explicitly stated as being allowed in the prefaces to all our new regulatory documents. This SMR license application guide was posted for comment at the end of July and will be soliciting feedback through the 28th of September this year. Our current focus is addressing challenges arising from novelties in design through pre-licensing activities. Our focus will change as units are deployed. One key consideration for this is tracking the evolution of the design as it continuously improves to address lessons learned over time. It is important to note that overall, the CNSC's existing regulatory framework is suitable for regulating SMR activities. Looking now to the technology vendors, the CNSC has been approached by vendors so they can better understand the requirements, expectations, and the licensing process in Canada. Through our vendor design review processes, the vendors have been expressing their intent to comply with Canadian requirements. CNSC staff have also observed that vendors are now actively engaging with existing nuclear operators. They appear to be soliciting utility design requirements. What an operator may impose on a vendor will be expected to address the regulatory requirements and also include their own considerations for operability and maintainability. This can impose more constraints on the vendor's design program. Currently, 10 vendors are engaging with the CNSC in the vendor design review process, which will be discussed in more detail shortly. I will now turn the presentation over to Mr. Christian Carrier, who will be discussing the CNSC's international engagement activities.
Thank you, Christian Carrier, for the record. We will now turn to international activities that the CNSC is participating and as related to small modular reactors and advanced reactors. The CNSC participates in a number of international fora related to licensing of new and advanced reactor technologies. Participating in these gives the CNSC solid benefits, and we are actively putting what we learn to use. These fora provide opportunities to discuss common issues amongst our peers internationally, share information where possible, and develop some common solutions. We feed what we learn into our continuous improvement initiatives to enhance our regulatory framework and internal management system. We are open to using both international research and other regulators' review to inform our own assessments. Opportunities are being taken in sharing resources, in conducting regulatory research and support, and development of training programs on new reactor technologies to support regulatory readiness. Using information that we have gained from international engagements leads to more efficient and effective technical assessment and gives us insights for planning both licensing and compliance activities. In terms of more formal international engagement, a number of fora exist with the International Atomic Energy Agency and the Organization for Economic Cooperation and Development's Nuclear Energy Agency. Under the Nuclear Energy Agency, we participate into the Working Group on Regulation of New Reactors, the Multinational Design Evaluation Program, and the Group on Safety of Advanced Reactors. These groups focus on review and licensing considerations for new reactors and advanced reactor technologies. We are actively entertaining discussions and exchanges through bilateral arrangements with other nuclear regulators, such as the US NRC and the UK ONR. The IAEA is also actively exploring the implications of SMRs on its existing regulatory suite of documents. I will expand on the last two bullets in the following slides. CNSC staff are participating in bilateral and trilateral cooperation activities with foreign regulators. The objectives are to seek areas of potential alignment in regulatory framework, exchange on national experience and sharing of best practices, and look for further opportunities for cooperation and technical reviews. A memorandum of understanding was recently signed with the U.S. Nuclear Regulatory Commission to exchange unclassified technical information and to cooperate on aspects related to reactor designs, life cycle consideration, legislation, requirements, and guidance, and technical reports. We will continue to collaborate with our peers internationally to better understand how we can work together and support each other. One of our most active areas of cooperation internationally is the IAEA-facilitated Small Modular Regulators Forum, which allows regulatory discussions on issues specific to SMRs and advanced reactors. An ongoing project aims to understand each member's regulatory views on common issues related to SMRs, to deployment, and to capture good practices. This forum was established in March 2015 as a 2-year pilot project. Participating member states in the pilot were Canada, China, Finland, France, North Korea, Russia, the United Kingdom, and the United States. The pilot covered 3 topics, namely the definition of emergency planning zone, the application of defense in depth, and the application of the graded approach. It was completed in 2017, and the final report was published in January 2018. Work associated with this initiative has already been reflected in our processes as a result of our continuous improvement initiative. Having completed the pilot topic successfully, the IAEA has continued this forum, establishing 3 issue-specific working groups, as noted on the slide. These new topics focus on near-term licensing challenges. These working groups are not seeking to develop new or separate requirements for small modular or advanced reactors. Rather, the intent is to better understand the impact of the novelties on the existing framework and to develop common positions where possible. I will now turn the presentation to Mr. Daniel Duchesne, who will be discussing SMR technologies.
Thank you, Mr. Carrier. Good afternoon, Madame President and members of the Commission. For the record, my name is Daniel Duchesne. I am one of the Vendor Design Review Technical Integrators within the Assessment Integration Division. I will begin this portion of our presentation with a short overview of some of the reactor technologies that are under development and involved in the CNSC's vendor design reviews. It should be emphasized that the information presented are generalizations and not reflective of a specific design. The graphics shown on this slide represent one design of a molten salt reactor. There are many designs, but they all use molten salt as their coolant. The coolant can be a melted fluoride salt or a chloride salt. The design shown here uses a molten salt that also contains the fuel, uranium fluoride in this case. This fuel in salt arrangement is often called fuel salt. Other designs use fuel elements that contain ceramic, metallic, or molten salt fuel. This particular design uses a graphite moderator core with vertical channels, and the fission heat is generated when the fuel salt flows through this moderator core. Molten salt reactors can also be designed without a moderator to slow the neutrons down. The generated heat is usually extracted through heat exchangers that are submerged in the molten salt. For these designs, it is claimed that the molten salt coolant has good fission product retention, is very resistant to high temperatures, and does not need to be pressurized to stay liquid, as is typical for water-cooled reactors. Another type of reactor technology uses a high-temperature gas as the coolant. The gas used to cool the reactor core is usually helium, but other chemically inert gases such as nitrogen or carbon dioxide have been used. This type of reactor uses tristructural isotropic fuel, also known as trisofuel. As the graphic on the current slide shows, the fuel is made of very small particles of uranium dioxide that are coated with various layers of silicon carbide ceramic and carbon. Each trisoparticle is about 1 millimeter in diameter. These encapsulated particles are mixed into an additional ceramic material and shaped into fuel pellets. The core of these reactors is composed of a graphite moderator block with many vertical channels. Some channels contain the fuel pellets, and other ones are empty to allow the helium gas coolant to remove the fission heat. In other cases, the trisofuel particles are mixed into a moderating graphite filler instead of a ceramic and are shaped into spherical fuel element about the size of a tennis ball. The balls are called pebbles, and thousands of them form the reactor core. These are called pebble bed reactors. For these gas-cooled designs, it is claimed that the trisofuel particles have strong fission product retention qualities and are very resistant to high temperatures, thus minimizing the potential for fuel failure and significant releases during accident scenarios. The graphics shown on this slide represent one design of a liquid metal cooled reactor. This type of reactor uses melted metal such as sodium or lead as the coolant and uses ceramic or metal fuels. They operate with fast neutrons and therefore requires no moderators. Like the molten salt reactor, the core is suspended in a pool or a vessel that is filled with the liquid metal, and heat exchangers are submerged in this liquid metal to remove the heat. For this type of reactor, it is claimed that the liquid metal coolants have good fission product retention, do not get damaged by high temperatures, and do not need to be pressurized to stay liquid. If we look at the diagram on this slide, item 7 depicts a human. This shows that some small modular reactor designs can be relatively large. Lastly, here is a diagram of a heat pipe reactor. This concept is usually on the small end of the output and physical size range of the small modular reactors. It is designed to use very few or no moving parts. Because of this, they are sometimes referred to as solid-state reactors. Depending on the design, they can use ceramic, metallic, or trisofuel. As per the example shown on the slide, the reactor core can be a graphite moderator block with channels for the fuel and for channels for the fuel and the heat pipes providing the cooling. The fast neutron design, for a fast neutron design, the core could be made out of stainless steel block with similar channel arrangements. The heat pipes contain a low pressure liquid such as potassium or sodium and extend outside of the core into heat exchangers. They passively remove heat through evaporation of the coolant in the core and condensation in the heat exchanger. This technology eliminates the need for primary coolant loops and all of the associated pumps and auxiliary systems. It is claimed that the cooling cannot be disrupted by pipe breaks or pump failures, and that the low number of moving parts ensures a simple and maintenance-free design. Vendors of all these reactor designs are claiming important safety features, which many regard as shaping the future marketability and deployment of small modular reactors. Several of these new designs are aiming to include the following safety features: a power level that is automatically controlled because of inherent reactivity feedback features in the fuel or the coolant, an automatic passive heat removal system using natural convection or conduction and requiring no outside source of energy such as electricity to help protect the fuel and the core from damage during accidents. A fuel that is not damaged by high temperatures generated during accidents and that retains efficient products during such scenarios. And a longer grace time for operator actions during accident scenarios when compared with current technologies because of the self-limiting power, the passive heat removal, and the heat-resistant fuel. As seen in the previous slide, the new designs are aiming at introducing a step change in safety performance. However, the claims have yet to be subjected to Canadian regulatory verifications. Evidence of the new safety characteristics and their limits will be required by CNSC staff. Consequently, we are very interested by certain areas or features of these new designs. Two examples of this would be the various passive heat removal processes used to protect the reactor core, or the inclusion of negative reactivity feedback to provide inherent power self-limitation. These safety features are not always easy to demonstrate, and they will have some limitations. CNSC staff will be interested in the methods used to understand and demonstrate these features and their limitations. Additionally, some of the new design concepts have challenges that are related to the lack of operational experience for the performance of materials in a new type of corrosive environment. There is considerable uncertainty when you only have short duration tests to support material aging predictions for component in a corrosive environment. CNSC staff will be interested in the approaches used to deal with these uncertainties. Also, a number of designs use integrated and sealed reactor modules that incorporate a reactor core, the heat exchanger, the pumps, the control mechanisms, and instrumentation. The enclosed and sealed nature of these integrated configurations could make inspections and degradation monitoring challenging. I will now provide an overview of the vendor design review framework and activities that are either currently underway or are scheduled to begin in the near future. A vendor design review, also known as a VDR, is a useful and valuable service offered by the CNSC and acknowledged internationally. While there has been recent increase in the use of the VDR process, it should be noted that it is actually a mature process which has been developed and adapted over the last decade. The current table shows the 10 vendors that are have recently engaged with the CNSC for vendor design reviews. The table aims to illustrate the ranges in terms of reactor type, power levels, country of origin, and status. Regarding the status, staff will be covering the difference in VDR phases shortly. The shaded area in the table are highlighting the VDRs that are ongoing. Of the 10 vendors, 6 have started or completed a phase 1 review, and the other vendors are in the process of developing a service agreement with the CNSC. Note that the progress of any VDR is impacted by the vendor's submission schedule, as well as the quality and content of their submissions. The first VDR on this list involves a molten salt reactor developed by Terrestrial Energy. The phase 1 review was completed in November 2017 and was a significant milestone since it was the first application of the VDR process to an advanced small modular reactor. In phase 1 review, this phase 1 review concluded that Terrestrial Energy has demonstrated an understanding of the intent to comply with CNSC requirements and expectations. The VDR is an optional process where a vendor of a reactor technology engage with the CNSC under a service agreement. Canadian and international experience has shown that early engagement with the regulator allows issues to be resolved prior to licensing, a process that can take years of effort in some cases. Stakeholders are therefore often encouraged to engage with CNSC staff at the beginning of their project so that they understand clearly the regulatory requirements they need to address for their planned activities. The VDR helps in the timely identification and resolution of key issues and fundamental barriers to licensing. It also facilitates the identification of research activities required of the vendor or the CNSC prior to licensing. It also provides an opportunity for CNSC staff to become familiar with the design and identify internal training needs. A VDR, particularly for new technologies, gives CNSC staff some time to consider what a proposal may mean from a regulatory perspective and to decide on a regulatory strategy, such as what set of regulatory documents will apply. Note that there is no licensing decision in a VDR and that it is not an approval of the design. The VDR process is described in guidance document GD 385 titled Pre-Licensing Review of a Vendor's Reactor Design. It focuses on the design and the safety analysis as performed by the vendor and includes all the supporting programs and processes. It covers standardized area comprising a wide range of subjects such as the reactor core and the fuel, the control systems, the containment, human factors, security, decommissioning, and many more aspects. Consequently, a VDR involves a wide range of expertise from many different CNSC divisions. It is important to note that in the event of an application for a license to construct, CNSC staff would use any available material from a completed VDR, but would also undertake a more detailed and comprehensive review to cover all licensing requirements. For example, this review would encompass all the full detailed engineering and technical analysis, qualification of the applicant, and site-specific considerations that would normally be out of scope for a VDR. A vendor design review is conducted in 3 phases. In phase 1, we ensure that a vendor understands and intends to meet the Canadian regulatory requirements. We look at how a vendor establishes the necessary information to support their safety claims, and how a vendor plans to justify any alternative approaches to meet regulatory requirements. Phase 1 takes approximately 1 year and 5,000 person-hours to complete. In phase 2, we go into much more detail, looking for any potential barriers to licensing and how the safety claims are being substantiated. Phase 2 is approximately twice as much work as Phase 1. In Phase 3, we focus on a few specific areas chosen by the vendor as requiring more work or additional clarifications following the Phase 2 feedback. Upon completion of each VDR phase, a confidential detail report is sent to the vendor, and an executive summary is published on the CNSC's website. The key lessons learned from past and recent VDRs include the following. The current regulatory framework is flexible enough to allow alternative approaches for meeting CNSC design requirements that may not be fully applicable to a novel reactor design. In such case, the accepted alternative must result in an equivalent or superior level of safety. When vendors propose alternative approaches to meeting the regulatory requirements, CNSC staff use these proposals as an opportunity to reflect on the current framework and suggest improvements where necessary. The VDR have positive impacts on the vendor design processes, including on their management systems and R&D programs. In summary, the VDR process is a very useful tool to reinforce regulatory requirements and expectations. It is a consistent and technology-neutral process that ensures all vendors are treated in the same manner. It provides regulatory feedback early on in the design process to allow potential regulatory and technical issues to be resolved prior to a vendor finalizing their design and before applying for a license. It also helps vendors to assess their technology's deployment readiness. It provides important information that can be used by CNSC staff during a license application. It helps CNSC staff readiness and also result in a more complete license application, thus potentially improving licensing efficiency. Note that design changes can always be made after completing a VDR. These changes would be reviewed at the time of licensing. I will now turn the presentation back to Mr. Robertson to provide some information on the CNSC's readiness strategy.
Thank you, Mr. Duchesne. Hugh Robertson for the record. Turning now to internal preparations, I will review the principles and activities that are contributing to the CNSC's readiness to review and assess any application for a license to operate any type of reactor design. To face these new challenges, CNSC staff have been working on an internal strategy for this fall to ensure that we are ready to regulate small and advanced reactors in a risk-informed manner. The primary objective is to enhance regulatory clarity and certainty by ensuring fairness, rigor, efficiency, and transparency. The supporting objectives are to ensure there is ongoing technical readiness, that we have the right people with the right knowledge and expertise, that there are appropriate management system processes with established priorities, and that requirements and expectations are clear to external stakeholders. One key element of this strategy is the CNSC's Small Modular Reactor Steering Committee. This committee was established to provide leadership to set the foundation for the regulation of SMRs. The mandate of the SMR-SC is to make high-level decisions regarding the regular position for SMRs, provide guidance and senior management support with respect to resource requirements, monitor progress against planned activities, track performance measures, and resolve issues as they arise. The readiness strategy is based on 3 pillars: a robust yet flexible regulatory framework, established risk-informed processes for enabling licensing and compliance decisions, and having a capable and agile workforce that is ready to meet the challenges these new technologies bring. The strategy has identified the tools and resources required along with areas for continuous improvement. Communication is, of course, at the heart of the strategy and plays an important supporting role for the 3 pillars outlined on the previous slide. Communication is needed between the proponents, the vendors, the public and Indigenous communities, the CNSC, and our international colleagues. This is a critical success factor and supports all other activities. In conclusion, small and advanced reactors do present new challenges, particularly with the various designs and deployment approaches being proposed. However, the Canadian regulatory framework is robust, flexible, based on decades of operating experience, and can be applied to advanced reactor technologies. Our framework allows for licensing not only new reactors, but also the various activities and facilities that are needed in new technology development and deployment for new reactor technologies. CNSC staff are working hard to understand and anticipate the upcoming regulatory work and are putting focused effort into ensuring our technical expertise is ready to support the assessment of these novel designs during the review of license applications. Both our framework and our internal processes are risk-informed, articulating our intent to regulate nuclear activities and facilities based on the degree of novelty, complexity, and risk posed by the proposal. CNSC staff allow for and appropriately review proposals for grading and alternative ways of meeting regulatory requirements. And we document the use of professional judgment during design and licensing reviews in areas that lack established codes or standards. Feedback from ongoing CNSC activities is actively used for continuous improvement. Vendor design reviews are a mature, well-respected, and useful service that is currently seeing an increase in demand. CNSC staff are actively engaging with stakeholders to ensure that our requirements and expectations are clear. Proponents are strongly encouraged to engage with the CNSC early to determine the appropriate licensing approach to be used. Additionally, we have identified areas for further discussion as a result of our stakeholder engagement activities. All that to say, the CNSC is ready and capable. We have the people, processes, and framework we need to license small and advanced reactors, while ongoing continuous improvement initiatives will enhance clarity both internally and to stakeholders. Thank you, President Belsey and members of the Commission. Our team is ready to address your questions.
Thank you very much for that presentation.